Is it working? Can you hear us?
So hope that we can see.
Yes, we can. We can see.
Okay, perfect. Perfect. Okay, go.
There's the gallery view.
It's okay.
It's okay.
Yeah.
Okay, so sorry. Okay. So hello. It's good to be here. We are artists and researchers.
And the structure for today's presentation, we've got two parts. First, we're going to talk about our concerns with AI and creativity. And then we're going to talk through how those insights carried through in our work Infranet.
Today, we would like to share our alternative approaches to AI creativity and art because of our concerns about the mainstream approaches to AI creativity and in general. And I think it has like some synthesize the points with Gretchen's greater presentation.
Yeah, absolutely. Like Gretchen said, the central concept of AI today is this optimization of prediction, and the risk of bias in data used to train AIs is being well documented. But we want to also look at some other risks that are inherent to the method itself. So first, there's a bias towards what can be measured and what can be approximated in general, at the expense of anything that's qualitative, anything that's rare, strange, or new. And obviously, there's a risk here of mistaking the map for a territory. And second, as we measure the performance and accuracy of an AI, there's also a bias towards a utility of what is known or what we think we know at the expense of the unknown and regardless of our changing world. So trained AIs therefore have these biases frozen into them, and this means bottlenecking the future into terms defined in the past, again, as Gretchen said.
Yeah, we want to illustrate these concerns with these like three example problematic perspectives: the problems of algorithmic specificity, objective functions, and anthropocentrism.
So the algorithmic specificity, most algorithms are effective at certain kinds of problems, but they're not effective at others. So for example, perceptrons are neural networks with no hidden layers. They can only learn linear functions, and they're incapable of awareness of a nonlinear space. This is just a simple example, but in general, algorithms have a structural bias. Their structure is an image of the problems that they are good for, but there's no free lunch. There's no optimization algorithm that can outperform any other on all possible spaces. There's no way to know in advance what neural structure best fits a problem domain. It has to be designed by trial and error. And since in most creative situations, the problem domain itself is not even known in advance, and for reality in general, it can be changing, there isn't even an ideal best candidate structure to be found, even though there can be many good candidates. So creative work in particular is dependent on its context and its time.
That is, the best algorithm is an algorithm that can rewrite its own structure to adapt to its world and can propose and evaluate many possible structures at the same time. Genes and neural cortices are examples of such structural plasticity and collective adaptation.
So next, the problem of objective functions. Training and optimization in general demands an idea of what a good solution looks like and a way of measuring how close we have got to that good solution. This is sometimes called the objective function, or sometimes cast as an error measure. Hill climbing and gradient descent are physics-inspired methods widely used in AI, using an objective function to search a space for the best scoring result. Evolutionary algorithms are sometimes used here too, as they can perform better when a search space is more complex. Then the objective function is called a fitness function. But this is far from natural selection. It's more like selective breeding. And in contrast, the creativity of natural selection emerges with no objective function, no fitness function, no measure of success defined in advance, no purpose, just a fuzzy set of changing conditions of viability, largely determined by the ecosystem itself.
Considering AI is pre-trained on a prior data set and an objective function defined in advance, the no-face character in Miyazaki Hayao's Spirited Away also came to mind. No-face was an initially small and voiceless god who nevertheless grew monstrous as it gave more and more and more of whatever it is that you show that you want, seemingly unable to understand anything else.
So in contrast, we looked at algorithms that avoid use of fitness or objective functions altogether. For example, the novelty search algorithm here has been shown to outperform fitness-based measures in a variety of situations where the problem domains are complex and resistant to optimization, or they're just generally open-ended. In this case, candidates are selected not by goal-directed scores or measures, but simply because they did something that hadn't been done before. And more generally, we're looking at methods that avoid external pressures and focus instead on intrinsic motivations. So in our new work, we're now looking at models of artificial curiosity, for example. And finally, the problem of anthropocentrism. So what trained AIs already achieve can appear amazingly human, but here there's also a reminder to be aware of our own anthropomorphic biases. For example, at first, this image captioning artificial neural network appears to have remarkable human-like common sense, understanding the content of the images. However, when you look at some of the contrary images that still produce the same confidence score, it reveals how what the AI sees is far, far more alien.
Here are more examples of those kinds. The point here is not that the image recognition AI is weak. The problem is our human centrism in seeing what we want to see more than we see the facts around us. Even though science has frequently shown that human perception is also far stranger than what our common sense assumes. That is, we generally have consciousness bias, including rationality bias, despite the vast evidence that the majority of cognition is neither rational nor is it conscious. In our current age of AI, this Jenny Hertz's 1982 statement has never been more relevant. Maybe we can change it to the sentence that they protect us from what we want.
So to help step away from anthropocentrism and algorithmic and utilitarian biases toward a more naturally created cognition, we found it helpful to think about Henri Bergson's distinction between quantitative and qualitative tendencies. So on the left here, we've got the differences of quantity. These are the dominant tendency of matter and space to relax into a kind of entropic equilibrium. And this tendency makes the distributions generally predictable. They can be easily approximated by a few parameters. This is something that is easily measurable, exchangeable. When it changes in number. But the characteristic tendency of life and the creativity of time is an intensification of complexity. It's an increase of heterogeneity. It's the creation of organizations that resist generalization, that become difficult to predict. These are non-equivalent differences, such as speciation. When they divide, they create differences of kind. So in general, natural creativity is a continual production of new qualities.
So now we are moving to our research creation. Artificial Nature is our ongoing research creation collaboration and installation series since 2007. Before moving on to Infranet, we would like to show common attributes to most artificial natures. The first, this is an interactive system art, especially seeking for infinite feedback, as we can find from any living systems and their surroundings in nature. Second, we aim to realize shared realities to bring non-human perspectives and to emphasize the overlapping surroundings between humans and artificial beings. The diagram is based on our flat ontology of human, non-human, and man-made beings, and the interweaving between virtual and physical worlds. And finally, with our artwork Infranet, we use neuroevolution to explore creative AI for a wild future. Here are our research questions for Infranet. The first question, what is intelligence for a living system? This is an ontological question, taking inspiration from natural creativity and cognition, and it naturally kind of linked to move to the second question, that what kind of relations between the artificial intelligence and artificial life are. And then, of course, like to create this art installation that how to build this AI and artificial life world as a world making.
So Infranet, the work that we're going to talk about now, this is work that combines real-world open data resources with evolutionary neural networks and extends the space of its complex adaptive system to the scale of a city.
Each exhibit of Infranet utilizes public data available on the host city, including Gwangju, South Korea, New York, USA, and Vancouver, Canada.
However, this is not a data visualization. Rather than revealing the data by answering human questions through data, Infranet treats the data as a habitat for artificial life, whose intelligence emphasizes intrinsic qualities and non-utilitarian perspectives. So none of the city data is directly displayed. Rather, what can be seen are thousands of moving creatures and the traces that they leave in the space. These dynamic trails thus draw out their own particular umvelts, revealing whatever the creatures intrinsically find interesting and the kinships between each other. That is, the data is not there for us, it's there for them. The population of thousands of creatures forms a diversity of biases. Each creature explores according to a unique neural network, different one for each creature, and also a unique taste or bias, which we represent as color. And this taste makes them insensitive to most of the kinds of data. Some might be more interested in waterways, others might be more interested in crime rates, for example. But for any particular creature, the majority of the data just doesn't exist.
These creatures are also curious and excitable as they sense each other's trails and make links to synchronize with neighbors. And in doing so, they are also influenced to change their tastes, adapting to their unknown feature. As they move and kinships change, tastes never stabilize. Instead, linear, circular, and spiral waves can be seen in the population you can observe.
So reflecting our concerns with static measures and with algorithmic biases, in Infranet, the creature's neural networks do not have a predetermined or even a static structure. With each pulse or chirp, they sing their neural structure, and a neighbor can pick up this song with mixing it with their own neural network or just adding mutations to produce a new neural structure in themselves. This is a little bit like the continuous genetic exchange of bacterial quasi-species, or perhaps also the contagious diffusion of ideas. Over the population, this change happens thousands of times every second, and thousands of completely new neural structures are found every minute. We consider this as an artificial natural evolutionary system. There is no fitness function, there's only a viability condition, which is defined as a measure of a creature's well-being, which is replenished whenever it senses data to its taste and when it senses the trails of others. Put simply, the creatures have a primal need to verify that the world still exists and that they're not alone in it. This, however, is a very weak selective pressure. We measured an average lifespan of the creature well over 10 minutes, allowing them to more freely explore the natural dynamics of the system. And a creature can change its neural network on the order of 100 times within that lifetime. More significantly, there's an intrinsic drive towards a qualitative change. So creatures with lower well-being are more likely to adopt or copy or mutate the neural networks of their neighbors, especially if their neighbor's taste is different.
This is the second the visualization. We call it as a watcher. It's the bio-CCTV on immune system. Each watcher follows a creature as it moves through the data, displaying information about the creature's current state and similarity to their neighbors. The intention was to locate any stagnant monocultures.
So to close, it seems that AI will become ubiquitous, if it already isn't, smearing like new media to all aspects of life, into what Catherine Hales described as a planetary cognitive ecology. We are therefore cautious about relying on static performance measures and assumptions in creating AIs. The risk of overdetermination by the low-hanging fruit of available data, readily measurable properties, known structures, and so on. We don't want to live in a future that's already paved by the past. This seems characteristic of a more general human tendency to displace anything that we can't measure or make use of, like dominating a market, but also leading to our current situation in which nearly all of Earth's biomass is now in human service, despite the fragility that inbreeds.
Instead, we hope for a planetary cognitive ecology that foregrounds creativity in the natural sense. This points to the value of creativity beyond art, oriented to an open, adaptive, and anti-fragile future. We hope that a better understanding of creativity beyond the human-centric may point again to qualities of the wild.
So we should not assume that we have a coherent grasp of what creativity means in the human case. And second, we should not limit our investigation of creativity to human standards. In our view, what is impossible is not machine creativity, but the division between machine and nature. And what we're concerned is that if we try and focus on that impossible division, we'll end up creating the division by ourselves.
Thank you for your time and attention, and we look forward to sharing your thoughts.
Oh, thank you very much.